Good evening, everybody. Welcome to the A-Level Computer Science live stream for the Component 1 exam, which is on Monday the 13th, I believe. Just wait for a few more people to arrive. Hopefully you can hear me okay. If you can't, I'm sure you'll tell me when you hear nothing. Hello, Georgia. Hello, Suhib. Almost with us. There's a surprise. So the point of tonight's live stream is to go through component 1. We're trying to get that out of the way first. Just remember, people, that there is also on Friday from 9 till 11, there is a revision session. That's drop-in. It's not compulsory. You don't have to come to it, but you're more than welcome to come to room 242 in the college, and I'll be there as well as other computer science teachers. Hello, everyone. Hello, Rahul, Isham, Mariam, Zakia. Hello. Oh, and Cameron. Sorry, I forgot you there. Okay. Please feel free to interact with the chat as well. You know, fire your questions in there. I'll do my best to answer them. And I'm just going to go through the advanced information stuff today. And if people want to see a little bit more, they can do. The presentation that I go through today as well, that's also going to be sent out for you all as well. In addition to that, I'll be sending out a poll as well. I'll be sending out a poll for Component 2 because I'll do another live stream for Component 2 as well. Sorry, Adil. Electronics exam. I know. There's nothing I could do about it, unfortunately. Hello, Victoria. Wonderful. Just waiting for a few more people. Wonderful. Oh, we've got some decent viewers now. That's good. I did say hi, Cameron. Right, so let's jump straight into it then. Time is of the essence. We'll try and get this done. Hopefully this won't be a big epic 4-hour live stream. I'll hang around for questions at the end. So let's kick off then. And let's start our live stream. So don't forget, 13th of June, it's an afternoon exam as well. So check on CEDA because you'll have your seating arrangements on there. I'm sure you've already done exams, etc. Computer science is quite late, to be fair. But it is a 2-hour and 45-minute exam. So I did say in class you won't need all that time, but do take your time in the exam. It is stressful. It is a stressful situation, and your brain does not respond very well to stress. Okay, so please do take your time with that. Now this is only component 1, and that's our advanced information. Please, if you have not seen that, where have you been? Where have you been? There are 6 different sections on there, ranging from data structures all the way to our economic legislation stuff. That is not all that will be covered in the paper. All right, we saw that from the AS programming exam. It's worthwhile looking at other parts as well, but that is your main go-to content that you're going to cover for this exam board. Now, your section titles have been provided. They're the topics. On the right-hand side, you've got your amplification material. So that is the underlying areas inside those topics that will be covered as well. So here we are. This is everything in our A2 component 1. So these are our different chapters. And everything that's highlighted there are the things that are on the advanced information. So not a lot has been covered by the advanced information. So there will be other questions from other sections as well. So let's get straight into it with our data structures. And we're going to kick off here. So we've got arrays up to 3 dimensions. So that's 1-dimensional, 2-dimensional, 3-dimensional arrays. We've got records, stacks, queues, trees, linked lists, and also hash tables as well. Now, from the survey that I sent out to the students, they told me that hashing tables is something that they really want to cover, and that queues and stacks often get confused. Trees, you're fairly happy with trees and the traversal stuff, but linked lists, we learned from the mock exam, there's a good question in there. A lot of people lost a couple of marks on it, but I'm sure we're much better than that now. So let's fire on then. So with any data structure, we've got two categories of data structure really, and that consists of our static data structures where the size is set at the beginning of the program and cannot be changed. It's very limiting and inefficient because we can't expand and contract our data structures as we need them to be. But static data structures, they're easy to program and they're easy to manipulate. And by that I mean add information or remove information to and from. Whereas our dynamic data structures don't have a limited size. They can expand and contract as needed, but they're more complex to implement, and also they have a larger memory uptake potentially in your system, because you're going to have to keep adjusting for how much information needs to be stored in your dynamic data structures. So we kick off with arrays then, okay? Now arrays are the simplest form of all data structures. And what an array is it's a collection of variables, or elements as we call them, and they all have the same data type, and they're all grouped together under a single identifier. So each variable in the array is called an element, and it's accessed, you access those elements using its index position. And I'm sure you can all tell me what position arrays start at. And that's obviously position 0. Now, do not get them confused, because Python has these things called lists, and lists work in exactly the same way as an array, but in a list they have different data types in there. That is Python specific, okay? Not all programming languages are like that, but in data structures, all arrays all have the same data type. Now, fine, one-dimensional arrays, no problem with that. Two-dimensional arrays, it starts to get a little bit more tricky, because in theory you can have arrays with a large number of dimensions. You can keep going. You can keep going up to whatever dimension you want, but for A-level we only go up to 3 dimensions. So here's some code to show you a 2-dimensional array. Now if my presentation works here, you can have a look and see that you've got Sam, Lucy, James, Jack and Jane. They're inside one array. So there they are. Sam, Lucy. It's pretty difficult to draw on this screen down here. Let me see if I can do that. Yeah. Sam, Lucy, James and Jack. And they are all in row position 0. So this is their array at position 0. So 0, 0 would be Sam. 0, 1 would be Lucy, 0, 2 would be James, 0, 3 would be Jack, and 0, 4 would be Jane. That's their coordinates. Then we've got a second array. So Peter, Sarah, Adam, Karen, and Verity, they are on the next line. And you've got Emily, Edward, Dominic, Justin, and Jake. Now a 2-dimensional array works just like a table with an X and a Y coordinate. So here we go. Print names 1, 2 would print the word Edward. Okay. Now, within this, we have 3-dimensional arrays that get even more complex than this. Okay, so we get even more complex than 2-dimensional arrays, because what you've got here is you've got basically 2-dimensional arrays within another array. So here you can see, the way I picture it, or the example that's given, is you've got a tutor group and a name. So you've got multiple groups, or classes, for example. Okay? So now what you'll see Sally, that's the name. Tutor group is in 7TU and it's separated by a comma. You've got Bert and then 7AB. Now look at the brackets, because they are individual arrays themselves. Okay, so if you think about it, you've got 0 and 1, and you've got 0 and 1. Down here, Martin's got 0 and 1, and 0 and 1. Okay, now all of that, those two-dimensional arrays are wrapped up in one larger array. So there's one array here, one array there, two arrays there, 3 and 4. But look at where the brackets are. So Sally, on this second bracket here, I don't know if you can see that, it's very small. And this one, they are wrapped up in their own array, which creates this separate table here. Sorry about my bad drawing. Martin and Susan, they're wrapped up in their own array there. I wish it'd stop doing that. I'm not right clicking, I promise. They're wrapped up in their own array. And then you've got the outermost brackets, and that contains everything together. So it brings them all in. So a single row in each table can be represented by a one-dimensional array, for example, Sally and 70U. The entire table can be represented by a 2D array, that's the name and tutor group. And then as we have 2 classes worth of data, we can move to the third dimension by expressing the final array as being a set of classes. Now, as you can see there, we're only up to 3 dimensions, and it gets hard to visualize at this stage, and that's why we tend to stop. Very rare that you see anything more than 3 dimensions, to be honest. And will you be asked to program or pseudocode something in 3 dimensions? Very unlikely. I've never seen it to be pseudocoded. You might have to explain why we might use 3 dimensions. And the reason why we do use 3 dimensions is to group data together, group 2-dimensional arrays together under one identifier. Okay, it's all about the organization of information. So that's 1, 2, and 3 dimension, or 3-dimensional arrays. Hello, Johnny. Now, records. Now, a record is a set of data that's all related to one single identity. And you might say to me, well, John, so is an array. Yeah, it's lots of different elements under one identifier. Well, you would be right. But the difference with records is that a record is a collection of related fields, and those fields can be different data types. For example, here we've got our field names, which we've got member ID, first name, surname, gender, date of birth, and we've got data type, integer string, string, character, and date. Okay. Now, simple. Records are quite straightforward, and you should be used to records if you've done file handling with me before in your coursework, for example, because as you know, records make up or are a part of files. So we have lots of different records in files, and records contain fields, and inside files there are records. Quite straightforward. So if you want to get around the problem of having one data type in an array, each one of these boxes inside your records here, it could have, if you wanted to, you could have an array in those there. So you can have an array of records if you wanted to. So I could say, here's my array. Apologies how bad that is. And you could say, oh, well, in here contains a record with my member ID, first name, surname, gender, date of birth. And I'll have another record inside there, another record inside there. And that's the reason why we can loop through a file and bring all the records and put them in an array. Okay. Now, if you've got any questions, people, do fire away. I'm just flying through this. So if you've got any questions about anything, do put it in the chat. So the next one we're looking at is a stack. So a stack is a last in, first out data structure, and adding to the stack is called pushing, and taking off the stack is called popping. And then stacks are implemented normally using arrays or even a linked list. Okay, when we get to linked lists, you'll see that they're quite universal. We use linked lists to implement a lot of things. Now, the point of most of these data structures is the fact you have indexes in which you can use them as pointers. So here, what I'm going to show you now is going to show you a bit of code. And the reason why I'm showing this code is because people asked about how to program pushing and popping from a stack, because that's where we normally see questions. So for example, here's my stack here, and I've got Edward, and this is implementing a stack using an array. Okay, so 6 elements in total, and we've got a procedure that's called pop. Now this is Python, I can tell, because it starts with def and it's got its indentation, blah, 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 blah. Now, to pop it off, okay, it removes the value from the top of the stack and returns it to the user, right? To the graphic user interface, to the command line, whatever. Now, pointer top, okay, it says is 3. So I'm looking at position 3 as the pointer top. So here it's Sam. Now, why is position 5 not the pointer top? Does anybody know? Why is position 5 not the pointer top? This one. Any idea? Oh, people didn't plan for questions, did they? Because it's empty. Exactly. It is empty. Yep, points to nothing. It is nothing in it at all. Now it says value, so this variable called value is going to be given or assigned the value of my stack, which is this, at the position of pointer top. So inside value now goes Sam. So Sam goes in there. My stack, pointer top equals empty, so that gets crossed out, and that says empty or null. And then pointer top equals pointer top minus 1, so it goes from 3 down to 2, and now it points at Peter. Okay, so you've got Edward, Emily, Peter, empty, empty, empty. And then it says return value, and that means return Sam. Okay, now that might seem quite difficult to get your head around in an exam, but think about it logically. You are pointing to the top of your stack. That is the first thing that's going to come off. Okay, so what you have to do is you have to first record the top position, take what's on there and pop it off into a variable so you can print it out, then set whatever you're pointing to null or empty, and then decrease the pointer top. Now when you're trying to put something on there, all you have to do is when you push in, don't forget you need the data. Okay, so let's say I had the data was John, speech marks. Then you need the pointer top. So what is the top position of the pointer? So let's take Sam again. So that's 3. So that's pointer top is 3. It says pointer top equals pointer top plus 1. Well, if pointer top's 3, then that means that was position 3. This is position 4. So now pointer top is pointing at 4. And then it says my stack at the position of 4, which is pointer top, is given the data, which is John. So it's even more straightforward. It's less lines of code, and it just says replace empty with John. That's what that code does there. Okay, that's just some sample code that we could run if we want to. And this here, right, if you wanted actual pseudocode, all you'd have to do is get rid of this. You don't need these. You don't need them. You don't need that. And return's fine. That's it. That would work perfectly fine for pseudocode. Python is such a high-level language that it almost is. Some exam boards like AQA and OCR, they allow you to write directly in Python in the exam. Okay? Any questions on that? Questions? Nope. So that is our stack. Pushing and popping. Peeking is okay, but you don't need to know it for this exam. No. Wonderful. Now, queues. I can post the slides later. Yes, I can. You know, if you need to go and have your dinner or whatever. Queues. Okay, queues. Whereas a stack was a last in, first out. Okay, queues are first in, first out. So think of queues like the ones you find at supermarket. All right. If somebody cut the queue, you'd be pretty miffed. All right. The first person in the queue is the first person to leave the queue. So this follows everyday, just natural British order. Okay. Nobody likes queue skippers. Now, here is the same thing. Python code again. And this time, this is showing you two methods. It's showing you enqueue or dequeue. Now, when we say pop, okay, that actually means dequeue, which means get off the queue. Push means enqueue, enqueue. So push them on, right? So we're back to our array again, implementation. We've got Sam, Peter, Emily, Edward, empty and empty. So now we need to take one off, okay? So who are we removing from the front of the queue? Now, when we're talking about queues and the front of the queue, we always start at this end, the least significant or position 0. That is our pointer front, okay? I'll put pointer front, okay? So we're actually looking at getting rid of Sam. A lot of students go to the end here, go to like Edward. That is not correct. Not for a queue. Okay? So then, same thing as before. Value equals my queue pointer front. Does anybody know who is in my queue at the position of pointer front? Give me a name, people. Give me a name. Who is in my queue at the position of pointer front? Pointer front is 0. Well done, Sam and Georgia. Yep, that is Sam. So Sam goes in there. Excellent. Oh, look at you. We're firing. Yeah, even Yamin's getting involved. Look at that. Now, my queue, pointer front equals empty. So that means we replace Sam for empty. Okay, some people can look at this and go, yeah, this is obvious, but some people can't. Then it says pointer front equals pointer front minus 1. Interesting. Minus 1. Then it says return value. Okay, so then we return Sam. Now think about it. Even though pointer front is set to minus 1, okay, next time round, if we wanted to get rid of another person, okay, the pointer front would get set back to 0 again. All right, every time it would be reset back to 0. All right. Then you've got def push, data, and that's why we ask for the data. So whenever we ask for the position so that we can actually put data on or take data off at certain points. So push requires data. So if I was going to push John onto the list, the pointer back, does anybody know what position, what number would be pointer back? Pointer back, what number, index position would that be? Where is the end of my queue? Number 4 is I'm saying 6. 4. Okay, it's actually the empty position in my list here, which is 4. Okay, so my queue pointer back 4 is given my data, which is John, so gets rid of empty and it puts John in there. Then it says pointer back equals pointer back plus 1, so it increments the pointer from 4 to 5. So now we know that this is the back here. Okay, and that's it. And then again, there's some code that we're not really concerned about. That was just to test it. And you could get rid of this. You could get rid of that. You could get rid of those. It doesn't matter if they square brackets. The examiner will still know that that is a list or an array, sorry. So we're all good. Okay, now, John, what if I use pop in my exam? John, what if I use push in my exam? Then do not worry about it. Do not worry about it. You could call them whatever you want. Okay, whatever you want. Doesn't back point or point at null. It points at the null position after the last data item. In the pop function, shouldn't it move all the others forward? Well, realistically, if this was a good pop method, okay, it could, one method. So I'm answering Johnny's question here. Johnny's asking, shouldn't this position 0 basically be removed, defunct? We should set this one to 0 really, and set this one to 1, etc, etc, etc. Well, there's a couple of different ways you could do this, to be honest. I mean, it's not great that they set -1, in my opinion, because they're trying to lower it. However, I would probably increment the front pointer and just use a front pointer. But the problem with moving this and setting the front pointer means that when this is null, you've got wasted space because you never add on to the front. So I would say to you, Johnny, I would move them all down. If I was coding this, I would move them all down into the new position. I wouldn't even put empty there. I'd just overwrite it. I'd move Peter over Sam. I'd move Emily over Peter. I'd move Edward over Emily, and do that. That's what I would do personally. So, but because this is a question, because it's pseudocode, we don't have to move anything. So we're all good. Are you allowed to shorthand? Yes, you are allowed to shorthand in pseudocode. Yes. Okay. Now, moving forward onto trees. We have, what you've been looking at is actually two things: binary trees and binary search trees. So, why do we need to subtract 1 from the point if it's going to be set back to 0? Like I said, Abby, that there, I don't particularly like this, okay? What I would say, I would probably say, what would I say? For the purpose of this, I would actually increment it by 1. That would be my personal opinion. And the reason why I would +1 is because I need to hit data every time. Because once Sam goes, Peter is now at the front of the queue, which is +1. Then when Peter goes, Emily is at the front of the queue. The problem we have with +1 is that it starts to put wasted space at the start, like I said. So if this was my exam, I would put +1 there. That's what I would do. Now, next time you run a pop, it's going to reset itself back to 0 because of this line here anyway. So realistically, Johnny was right. We should really move everybody forward. Only because it's a queue. Okay. Now what I'll try and do is I'll try and find an exam question later on with a queue in it for people. So, looking at trees, binary tree structures are made up of nodes. Okay? The nodes are put in a very specific order based on some rules. Now we call the nodes, sometimes we call them leaves or we call them links. Okay? Sometimes the connection between the nodes are called branches, and each node has a maximum of 2 other nodes coming off it. Okay? And what you're looking at on the screen is a balanced binary tree. Okay? Binary because there's 2 nodes, and the tree structure is balanced because we have a perfect split down the middle. So in here, between Sam and all the rest of them, we have exactly the same nodes on the left-hand side of the tree and exactly the same nodes on the right-hand side of the tree. So it's perfectly balanced. All right. Now, there are benefits. You might get asked about the benefits of having a balanced binary tree as opposed to an unbalanced binary tree. You might get asked to draw a balanced binary tree or draw an unbalanced binary tree. So be prepared for that, people. Now, binary trees are used to implement another data structure. So we take the binary tree that you're looking at on the screen, and then we turn it into something called a binary search tree. And that's where we use our traversal methods on the tree itself. Okay? They're identical to binary trees. So you just assume that they're the same thing, but they have an additional constraint. So a binary search tree is where the rules are brought in. The data on the left branch of the node is less than the data in the node itself, and the data on the right-hand side, the node on the right-hand side, is greater than the root node itself. Okay, they're the rules. Now, these rules are specified in a question. So when you get the exam question, it will actually tell you what the rules are. But just bear in mind that if the two nodes match themselves, so if the two nodes are equal, then the rules in the exam question will tell you what to do, whether to go left, which is usually the norm, that's normal. If the two nodes are the same, you normally go to the left. But that will specify in the question for you. Okay? Now, we've been through these questions before. I'm pretty sure you've been through these questions before. So I'm not going to go through them. I put these in the slides so that you can have a look at them. I will do a few exam questions though, but I've picked a few more obscure questions that you might not be used to. Okay? Now, we can take a binary tree and put it in an array. So unlike stacks and queues, there's a range of different ways to traverse a binary tree structure. And you know the three traversal methods. Yeah, we've got in order, we've got pre-order, and we've got post-order. Okay? So each method returns a different set of results. So it's important to get the right traversal method on the tree. So first, we've got something called a depth first search, which is a pre-order traversal. Now, I think you're pretty good at this. Okay, students seem to be okay with this. Okay, the rules, all you got to remember is node left right on a pre-order traversal. Now, like I said to you, when I've shown students how to do this, okay, I know that the first thing that you should write down is the node first. All right, so in a pre-order traversal, you should have the root node first, which is D. Yeah, so if you put node left right on each one of these, node left right, node left right. Okay, and you go through the tree, and then you tick these off as you go, or cross them out. Yeah, I've got the node now. Got the node, so I'm going to go left. Yep, go left, and then you start the new block again. B, scratch off the node because you're going to take that, so that's B then. Fine, go left again. Node, okay, I'm going to take A. Go to the left of A, nothing's there. Scratch that off. Go to the right of it, scratch that off, nothing's there. I've done node and left now. I'm going to go right. Then we go to C, etc. That's the node. Left and right I've done because there's nothing on either side. I've done the right hand side of that now. Now I've done the left hand side of the tree, so I'm going to go to the right hand side of the tree, and then I go F first, and then I go E, and then I go G, and then that's it, and the whole tree's done. Okay? In order to do the traversal, you just have to take your time. The most common mistake that I see is not because students can't do this, it's because they feel confident with it and they just fly into it. Okay? Take your time. People make mistakes with this, and there is absolutely no need to make a mistake. It takes one wrong step for you to potentially get most of the tree wrong. So please don't do that. So pre-order, I should see the root node first. Okay, an in-order traversal, the node is in the middle. So I should see the D in the middle, left-hand side nodes, right-hand side node. The D should be in the center. Okay, and I think this one gives A, B, C, D, E, F, and G, I believe. And then your post-order traversal, post means at the end. What's a real-life example of pre-order? A real-life example, what do you mean? What do you mean, real-life example? So in our post-order traversal, the node should be at the end. So the root node, D, would be at the end. And then you'd have everything on the left-hand side. So this would be A, C, B, E, G, I think it's F, and then D. Yep, I think. Yep. So you will get these questions through these traversals are normally worth 2 marks. You get 1 mark for all the correct order of the nodes, and you get 1 mark for the correct root node. Don't you have to show examples of when traversal methods will be used? Not necessarily, no. Nope. I personally don't remember a question where it's asked you to talk about real life traversals and what real life examples. If it's not balanced, you can have a look at something like that. Okay. If, for example, if we do like a pre-order traversal where we've got node, left and right, it works in exactly the same way. So you've got node, left, right. That means you're going to take Phillips down like that. I'll put Phil. Then you've got this funky, I think it's German, funky German TV manufacturer, Blappunt. You have Phil, then you got Blappunt, like that. So you've done the node, Then you can't go left, okay? So because there's nothing there, you just scribble that out and you continue down the right-hand side. So then you go Panasonic, then you go LG, and then you go Hisense. Okay? So you just continue on as normal. If it doesn't have it, you just don't take it. That's all. Only being a question asking in a filing system. Let me know what question that is, Omer. Let me know what question. Okay, so there's loads of examples in here that you can follow through. But what I really want to talk about is stacks and queues. Just like stacks and queues, with binary trees, you might have to represent them in a two-dimensional array. Okay? So we need to have a look at this. Thanks, Omer. I think I've got that question. I think I've got it. I think we're going to do that today. So using a linked list, the nodes of a tree are made up of a piece of data as well as pointers. So let's have a go and look at one of these. Let me just skip to the questions. Right. Let's just have a look at this one. Before we get into some questions, just want to have a look at this. Binary trees, removing nodes. It's very rare we see a question on removing nodes. Okay, you're normally going to have to draw this. So if you look on the screen, removing a node is very simple if it's the last node. Yeah, you just get rid of it, no problem. Remove it, off it goes, chop it, chop it, chop it. It doesn't affect it in any way, right? We've moved from a balanced binary tree to an unbalanced binary tree, okay? But then, an element is removed from the binary tree and the necessary branches are updated, okay? So if you look at this, you've got B here being removed. Then if you just chopped off and removed the pointer from B, you would lose the entire tree. So you have to connect the lower nodes as much as possible, okay? Now, if, for example, the exam question wouldn't ask you or wouldn't tell you to just like, well, get rid of F. What would you do if you got rid of F? Right, it wouldn't do that. What it would do is it would normally give you an unbalanced tree like this. And it would ask you to, let's go with this. It would say what would happen if you removed G, for example. Yeah? Then Z would connect to F. Okay, what happens if you removed F? Then Z would connect to D. Alright? As long as you keep the nodes, the lower nodes, because if you don't, you'll lose them. If I just chop this off, then you would lose this node, this node, this node, and every other node attached to it. So bear that in mind, people. All right. I'll come back to trees. Just so we know, we've done loads of questions on these, and I've judging by the survey, people felt pretty comfortable with these. Okay, just remember, because in the quiz, a lot of people made a few basic mistakes with this. Here is a question that talks about binary use using pointers. So a binary tree can be constructed using the following rules. So you've got your 3 rules. The first item becomes the root earlier or at the same position in the alphabet, goes to the left. Later items in the alphabet go to the right. Draw a representation of a dynamic binary tree with pointers using the following data. Show how the tree could be represented using a 2-dimensional array. Make the following amendments to the tree represented as a 2-dimensional array. Insert new key and delete Warrington. All right. Now this thing on the left-hand side, that is your index from your array. We start at 0. Think of it like an array on its side, similar to a stack, believe it or not. Newport has a left pointer of 1, which is Canterbury. Okay. This one, Warrington, for example, has a left pointer of 4. 4 is the index for rugby. Rugby's left pointer is -1. Does anybody know what -1 is? If the left pointer is -1 or the right pointer is -1, what does that mean? Exactly. It means null. Okay? If you put null in there and write null, you will still be awarded the marks, okay? However, if it asks for an index position, really, you need to stick to numbers. Do not risk it. Okay, you got to stick to numbers. So -1 is sufficient. Don't put 0, please, because that means the start position. Newport is at position 0, and that's the root node, because that would be wrong. Okay. Now moving on to linked lists. It's probably one of the most common data types. They are dynamic. You don't declare the size at the beginning. It expands and contracts as needed, just like a choo-choo train. Okay, you add more carriages on, you take more carriages off, no problem. Okay, they're made up of nodes, and each node is linked to the next node. There's 2 parts. You've got the data and you've got the pointer. The data is what's carried in the node, and the pointer points are connected to the next node. Choo-choo indeed. So linked lists are used to implement almost every other data structure. They're very, very popular because of how easy they are to manipulate, add on and remove things from. All right. So there we are. Nodes that consist of a data and pointer. Now I'm going to show you some code. Please don't be afraid by the code. Johnny, it's 9 a.m. in the morning. Okay. So let's add a new node. Now this looks terrifying, doesn't it? Right? Don't worry about this. The star here just means a pointer. So it says node, which is like a class. So if you remember object-oriented programming, node is a class. And we're creating a new class called new node. And it's given the value of new node. That might sound strange, okay? A pointer is given to a new class and it's got a new node. So all that's done is created this. Then the second one says new node. It calls the method from the class called setData. Okay. And then it says put Dan in there. So Dan's in there now. Right? We've not set the pointer to go anywhere. It's not connected yet. It just creates a new node called Dan. So create a new node and give it the name of Dan. There's our existing linked list. So we need to put that in now. So it says if something is true, current head, set next, new node. So current head is basically where Edward was. Then it says set next and it gives new node, the thing we've just created, and it sets that and puts Dan on it. All right, so 3 things you got to do. 1, create the node. 2, give the node some data. 3, connect the node to your linked list. And that's just like appending. Appending is adding to the end, isn't it? So in this one, what if we need to add Julie? So, adjust the node that is currently there to point to the new node, and then telling your new node to point to the next node in the list. I don't know how long we're streaming for tonight. We'll try and keep it short. I'm not even through the first topic yet, unfortunately, but we'll fly through. We'll keep moving. So, you're going to be asked to do this diagrammatically. If you look through the all exam questions document, you're going to be asked to do this on diagrams. There's loads of examples in there. Okay? Just remember, people, that when you're trying to connect or add somebody new in, first, this should be like this. You need to make the connection first and then delete your connection after. Removing is just as simple. So you just need to adjust the pointer and remove it. So if I wanted to get rid of Julie, for example, I would connect to Peter again, and then I would remove the pointer here, remove the pointer here, and I've now removed Julie. If I wanted to remove Edward, I would then take my pointer from Dan, connect to Emily, and destroy the pointer between Dan and Emily. All right. Now make sure you do connect the pointers. Don't draw lines between data, people. All right. Okay. This one is the one that people ask me to go through and talk about mainly. Okay. Hash tables. Hash tables. Now, a hash table is closely related to hashing algorithms. You've heard that word before. It's a very, very fast retrieval of data, okay? It does not matter about the amount of data that you're trying to store. It returns and finds the data at exactly the same time, all the time. Big O order of 1, okay? It's got a constant time. Big O order of 1, okay? Now, that's why people like them, because it doesn't matter if you have a bajillion items or 15 items, it will always locate the data in the same amount of time. And they're really fast. And they're really fast because they store data in what we call an associative way. It has a key and it has a piece of data, okay? So key and value pairs. And it uses a hashing algorithm to generate the index based on the actual the key itself. Okay, so the data goes in and it produces an index, and that's it. That's all it does. The index that's produced is a number, and hey presto, the number relates to some kind of index in a data structure. The hash table provides direct access to the array via a numeric index that is generated. All right. Let me break that down into really plain terms. You have a data structure. It's got 2 things. It's got a key. It's got a value. The value is the data. The key is the location. What we do is we take the data, we put it into a hashing algorithm that spits out a numeric integer that we can then directly access the array data structure to find the data, or to store it, or to retrieve it, or to do whatever we want with it. And that's it. Hash tables are used to organize and store the key pairs, the key and the value. All right? That's it. So, here's an example. To find someone like Lou, using a linear search would take a very long time if the array was very large. So if we know the index, we can find the position in the array almost immediately using direct access, where it is in the array at the start or at the end, it doesn't matter because the retrieval time is always the same. Okay? If we knew Lou was at position 3, we could just go output my array position 3, and then Lou would then be produced to my screen. Okay? It's finding that index position, which is the tricky part. So, like we said, yeah, remember the big fluffy cloud in the middle, data gets put into a hashing algorithm, and then the hashing algorithm gives us the location in the hash table where it is. Okay? Hash table has 2 components. A table where the actual data is stored, and then a mapping function called a hash function or hashing algorithm, which uses the data provided to find the index position. Two things. I'm just letting that sink in. Okay? If you've got questions, people, you need to type them. Fire away. Now, we are going to have problems in the future. Okay? Things like, what if we've got 2 items in the same location due to a dodgy hashing algorithm? Does anybody know what we do if we've got 2 items that have been hashed and they've produced the same index location? Does anybody know what we do with those things? Because it's a rubbish hashing algorithm. What do we do? Do we overwrite it? Ideal? I would say so, because they put hashing, because the data structures are on there, I would say you do. OMA, overflow area. A flag. Yeah, okay. So, you're quite right. We would handle this in a few different ways. Okay? Progressive overflow. Collisions created by the hashing function can lead to more records being stored in a single block. Okay, now we're moving into file handling now, people. So when I went through hashing algorithms with some groups, we talked about this, and we talked about how hashing tables from teacher 1 crosses over to me on file handling as teacher 2. So what would you say other than hash table is fast? It's fast though because it uses an associative array. And that, an associative array stores keys and values. Hashing tables are organized. Okay. Now, there's something else on the hashing algorithms as well. What was the other thing? Oh yeah. So if you say that an index is generated through a hashing algorithm, that would get you a mark. I saw that in a mark scheme somewhere. It's just stuck in my head. A numeric value. You have to actually say it's a number, which is strange, but there we are. Okay, so collisions get created, and each block has a maximum record count, and it keeps filling up. So your block in your file starts to fill up with all your data items, and then it goes over the threshold. The load factor in the block gets higher than 0.5, okay, or 50%. So there's 2 options that we've got. The first option is we can create an overflow area and place the records in there, or we can create a new file that contains more blocks and rehash every record to the new file. And that takes a lot more time than just creating an overflow. But if more and more data items are colliding because of your dodgy hashing algorithm, it's going to cause more and more problems down the line. It's better to create a new file early on with more blocks and potentially fix the hashing algorithm. Okay? So you could overflow it. You've got 2 types of overflow we're going to look at. Progressive, which means if the location is occupied, use the next available location. If the end of the file is reached, wrap around the block and start searching from the beginning again. So you basically continue to loop round in an endless loop looking for space in the block. Or you can use a flag overflow. So you can flag the original block and move the data into a designated overflow area. Now just remember though that your overflow in files are serial. Well, yeah, they are serial. They are placed there in chronological order. It's depended on there. So they have to be linear searched, and that is slow. Okay? So, question time. Have a look. Describe a queue data structure. Fire in the chat. How would you describe a queue data structure? What would you talk about? I'll tell you if you're going to get a mark or not for it. 2 marks, nice and simple. Describe a queue data structure. First in, first out. That will get you a mark. Yes. You could also say last in, last out as well, if you wanted to. Yeah. Oh, hello, Tom. Didn't even know you were there. Hello. Okay, where would you add data items? First in, first out. Example could be a printer. First in, okay. Now, I won't give an example here because we're being asked to describe a queue data structure. Okay, it's added to the back of the queue. Yep, so new items are added to the back of the queue, or you could say items leave from the first position and go. Okay, so if you talk about pointers or things like that, you will also get a mark potentially. So there's lots of different things you could say there for marks. Removal occurs at the top. I would also accept that. Yep. So then the next part says the following people are in an online virtual queue for concert tickets: Geeta, Sam, Hugh, Tarek, Joy, Fred, Casper, and Claire. Draw a clearly labelled diagram to show how the above queue can be represented using a one-dimensional array and pointers. So for this, nice and simple, a one-dimensional array looks like... Oh, that wasn't bad. I don't know why I did so many boxes. I regret it already. And I might say, well, in a queue, just remember, in a queue, this is our front, and this is our back. Okay? Now, realistically, for this example, I'd put the names of the people in here. So I'll just put the initial. Geeta, Sam, Hugh, Tariq, Joy, Fred, Casper, and Claire. Technically, the back would start here then, because that's the next available position where there is no one. So the back would be 8 and the front would be 0. Okay, so 1 mark for identifying the front pointer, 1 mark for identifying the back pointer, and then 1 mark for the representation of the one-dimensional array. That's easy, nice and simple. Problem here is accessing what they want, understanding what they need. Then it says, write an algorithm to remove a person from the queue or identify if the queue is empty. Okay, so if the, let's say I've called it front, haven't I? So if the front is not equal to, you could also use that. We could say back. So if the front's not equal to back, what should we call this? My array. Need a name. Okay. So that is saying, as long as the front is not equal to the back, that means there are things inside the array, yes? Then remove, pop something off, get rid of something, yeah? Remove a person from the queue. Now, in order to remove someone from the queue, this is where we're going to be removing them from in a queue. Okay, remember, queues always remove from the front. The front is position 0. So you would set the front position to null, and then what you would do is, for the people that were asking before, I would do this. Front pointer equals, that's a P, front plus 1. Okay, I've just moved the front pointer down because that person's now gone. Okay. Now, it also says, write an algorithm to remove a person from the queue, done that, or identify if the queue is empty. So I just need to say, else output queue empty, bracket, bracket, all right? End if. Now, how can I say that this else part is going to be the empty queue? Because if the front is equal to the back, that means these 2 pointers are overlapping each other. They're on the same pointer, which means the queue is empty because it's now in it, mate. Nothing in it. Two marks. Okay. And if we have a look, yeah, front, they call theirs front pointer though, but it doesn't matter. Mine's called back pointer. Front, back, array front null, front plus 1, array is empty. Okay, cool, that's fine, done. All right, now for time, let me go back. For time, what do people want to look at next? We've got Boolean expressions, searching, constructs. Constructs is pretty quick. Backus-Naur form, syntax diagrams, software engineering. We could do some Boolean on Friday if people need to. The meaning of life, constructs, yeah. Okay, Backus-Naur form, or Boolean Friday actually. Okay, 1.7, Backus-Naur form, 1.7 software engineering. Okay, yeah, Backus-Naur form. Legal. Okay, right. Constructs then. Come on, man, what are you doing? Yeah. Rubbish. There we go. Right. Constructs. People. There are 3 main constructs to computer science. Okay? It's the foundation, the fundamentals that we're all computer scientists are stuck on. All right? And they are sequence, selection, and iteration. All right? Iteration is also sometimes known as repetition, as you can see there on the screen. And 2 other things that I thought might be worth mentioning is a count variable and a rogue value. You've used rogue values before, you've used count variables before, but you've just not formally named them. So a count variable is an integer that keeps track of how many times a piece of code is repeated. So count equals count plus 1 inside a loop. It keeps counting, doesn't it? Yeah. For I equals whatever, 0, 2, something. Yeah. I is a count. It keeps track of how many times you've been through it. A rogue value, right? It says there, an invalid value to indicate a special case. Consider the word hello with each letter having an index. 0, 1, 2, 3, 4. The index of x is -1. Since the index cannot go below 0, this is a rogue value indicating the special case of x not being present in the word. Okay, so a rogue value is something outside the bounds of something. I think of a rogue value simply as a terminating condition. It's the thing that ends something. So for example, for I equals 0 to 10. Okay, when I get to 11, it's going to end. That's a rogue value. 11 is a rogue value. It's outside the bounds. All right. So if you get asked about a rogue value, think of terminating condition. Think something that's going to end something if it's hit. Okay. So let's have a look then at our three main programming constructs. We've got sequence, where code flows in order. We've got selection, which is if statements, and we've got iteration, which is repetition or loops. Okay. Now what I'm going to do is ask you what constructs we're looking at. I'm going to show you a piece of code now. Fingers on your keyboards. If you've got a mechanical keyboard, I don't want to speak to you anymore. There we are. What constructs do you see? What constructs have we got in here? Give me the line numbers as well if you can. Okay, we say we've got sequence. Whereabouts? A lot of people are saying Okay. Thank you, Hulbert von Ludwig. Mosin's here. Incredible. 8 to 11. Right. Wonderful. Now, this is it. There's only sequence going on. Now, believe it or not, people, sequence is occurring from line 2 to 5 because they get declared, they get created one by one. Number of trams, regularity of trams, number of staff, number of routes. They all get done one after another. Then, once we run this is actioned on an event. So only when it's called will it be sequenced inside here. Okay? One after another, they get done. All right? Nice and simple. What constructs do you see? Where do you see it? Isam says selection. Hulbert selection. Yeah, Zakia selection. Selection can't see the line number. Yeah, sequence and selection. Oh, okay. Yeah, right. Interesting. There is sequence going on here, people. There is sequence going on. Remember, we start at the top of the program, we work our way down. So from here, down here, sequence is going on. Then, we've got a standard selection statement with a logical operator in the middle, which is AND. And on this side, we've got an else if built in there as well. But it's still sequence. It's still selection. Still selection. So selection there. And we've got sequence in here. Okay? Don't get caught out with more than one. What have we got here? What do we see? Selection. Hi, Sophia. I don't know who these people are. Hello. Yes. Oh, Johnny, you are next level, my friend. Absolutely next level. Interesting. Right. So what we've got going on is, again, where's my pen gone? You cheeky sod. Right. Selection is going on. This here, there's a count variable for you. There you go, counting something up. We've got a message bot, we've got sequence going on, we've got selection going on. Johnny has said that we have nested selection, which we do. Nested selection is selection inside selection, which is good. Oma got a count there, good. You don't think you're the one that spotted that. What else we got? Yeah, sequence is going on again down here. So as you get better as a programmer, okay, looking at code, the more code you look at, straight away as soon as you open something like this, my eyes are drawn all over the place. So what I'm looking at, logical operators going on, count variables, inputs and outputs and stuff like that. It's all over, right? Just please bear in mind that nested selection was the key thing from that, which is an if inside an if statement. How exciting. Next one. What do we see? Good, yeah. Sequence again, yeah. First two lines, a sequence. I've lost my pen again. What is going on with the world? If line in now. Yeah, sequence and iteration. Well done, everyone. Good. So iteration, for loops, and while loops are your two main ones. Sometimes you'll have a do while, especially in Visual Basic, or a repeat until, or you can have a do loop until. Strange connotations. Python just has a for loop and a while loop, nice and simple, but there we are. Okay, what do we see in this one? What do we see in this one? Oh, very good. You're learning. Learning, people. Me trying to catch you out. It's got one piece of sequence, I suppose, in high number. But then you've got some kind of iteration going on and more iteration going on. So it's nested because this piece of iteration is going on inside here. And that is the real reason behind indentation. It's so you can spot things like that. The computer doesn't care about it being nested or not. It doesn't care about its indentation, sorry. Does it count as a sequence? If it technically does, because it's being completed on one line. Okay. If statements have a condition which directs you to a certain part, whether it's true or false, an iteration will continue based on a condition as well. So sequence doesn't do that. It doesn't have a condition it's based upon. So here's a question for you. Describe iteration. If I asked you what iteration was, what would you say? Whack it in the chat, people. I'm looking for one word specifically. Isam, not really. That question more was about the nested iteration. The question will ask you. It won't ask you just like what constructs are found. It would ask you to look for something specific. So state the lines in which nested iteration is occurring, for example. Right. Isam, looping is in the question. No, it isn't. Sorry. Looping is the informal term for iteration. But yes, Yamin, I'm looking for repeated, a deal. Yeah, that's right. Most incorrect. Yeah. Okay, Georgia. That's basically what recursion is. Now, iteration is repeating a set of instructions. Okay, for this 2 marker, you would say, when it says describe iteration, you would say iteration is repeating a set of instructions. That's 1 mark. Then you would say a set number of times or until a logical condition is satisfied. So in here, where is our logical condition being satisfied? Well, we'd continue until I reaches the n number. Okay, that's our logical condition. All right. Then it says, describe recursion. So we've already had it in there. So Hubert von Ludwig, whatever you called, yeah, and Georgia, they have already basically said that recursion is a method that calls itself. Okay, it's a function that calls itself within itself until a base case or a terminating condition is reached or is satisfied. So you'll see that's 4 marks. 4 marks. Thank you, Hubert. Now, the last one, okay, describe 2 advantages of using an iterative function compared with a recursive function to solve a given problem. Okay, does anybody know why we might use a loop instead of recursion? I would give a mark for saying that it uses less memory. Correct. Because recursion is going to open up multiple copies of the same program until it reaches the base case. That takes more memory. So we might use iteration. It is easier to code. That is also true. And I would give a mark for saying also that it is easier to understand or maintain. So I would take debug. That would also be in my mark scheme. Okay, so that's good. Most of the 4 marks are achieved in there. So I'll put the mark scheme in the program for you. So that is basically all of our constructs, sequence, selection, iteration. We threw in rogue values. We threw in count variables as well. You've spotted that in code, and we've also looked at a little exam question there. So let us fire back to the start. The next thing on the list was Backus-Naur Form. Okay, Backus-Naur Form, and mainly looking at why languages need to be unambiguous and syntax diagrams. So, why do we need programming languages to be unambiguous? Can anybody tell me why you might need your programming language to be unambiguous? Now, I've not explained what ambiguity is because I'm hoping you already know. Why do we need languages to be unambiguous? So developers can work together so they can be understood, can be interpreted in only one way. That's what I'm looking for. Because English is ambiguous, right? Natural languages, such as English, for example, they are ambiguous, and it's harder for programmers to understand. We're looking for the program to understand, so the computer understands your instructions to prevent misinterpretation, so it can run on different operating systems, interpretation in only one way, so computers can carry out the instruction. Okay, we're pretty much there, okay? Computers must understand a piece of code the same way every single time. Doesn't matter which computer's running it, doesn't matter which operating system's running it. It should. 100 viewers. Well, check me out. Check me out. Yeah. Where's my like charity button? Where can I say donate, like and subscribe, donate? Where's my donate button? Don't have one. Sorry. No, I don't. I just checked. I actually just checked. There we are. I did look at a YouTube video the other day, and it literally had a dollar sign that you could donate. I don't know how that person had that. Someone could tell me. Anyway, now then, unambiguous. Ambiguity is understanding something the wrong way. Oh. Deary me, people have. There we are. Okay. Ambiguity is the uncertainty of meaning in which different interpretations are possible. Okay, something's ambiguous, it's interpreted in multiple ways. That is not good for a computer. So imagine different computers running the same piece of code with the same inputs and getting different outputs. That would be a nightmare. Higher level programming languages must be unambiguous, so that there is only one way to interpret each program statement. Now, I am pretty sure, don't hold me on this, but I am pretty sure that it's going to ask you about natural languages and its ambiguity. I'm pretty sure on that because it was in the advanced information and it was quite specific. And you can only really go one way to this. So, natural languages, how are they ambiguous? Well, you've got things like having two words that sound the same. Okay? A homophone. Dialects or accents can be a problem. Understanding. The use of proper nouns. Proper nouns, mate. So if you've never done English before, then basically a proper noun, it's gone out of my head. What was it? A proper noun. So it's like a thing or a being. That's what it is. So that's what it's trying to explain or trying to describe. Now you've got words from other languages in common use. Slang also doesn't help. Voice patterns, so that's called intonation. So they're the things that we need to look out for. When it says natural language, that is the human interfacing with the computer. All right. Oh, just getting a bit of lag. Right. So let's then look at Backus-Naur Form, because Backus-Naur Form was brought in to remove these or to sort of sideline these problems. Backus-Naur Form is a grammar-free syntax. So it's a formal way of writing down the grammar of a programming language. It defines the rules that must be followed in order for source code to be syntactically correct. Any rules that are declared in Backus-Naur Form must be unambiguous. And it consists of three things: a set of non-terminal symbols, a set of terminal symbols, and a set of production rules. They're the three ingredients of Backus-Naur Form that you will be asked to create. Okay? Now, here is an example. Been through this in class loads of times. You'll be pretty happy with this. I have a digit rule, and the digit rule is assigned a value, a digit. Pretty simple syntax, but people got this wrong in the mock, okay? Mainly this bit here. Two colons and an equal symbol is an assignment operator. We have our rules surrounded by chevrons, and then we have our terminals in here. So terminals can't be expressed any further. Can anyone tell me what are the terminals we have? We've got numbers there. Anyone else tell me what are the terminals we can have? There's only three types. Anybody know? Symbols, thank you. Letters, yes, very good. Letters, symbols, and yeah. So numbers, letters, symbols. Okay, good. So symbols covers punctuation. Excellent. All right. So remember, we can have representation of a pipe. We can have multiple rules inside a rule. Okay. So here we've got a rule for 2-digit numbers, and that contains digit. Now, because these are non-terminal rules, it means we can express them further. So we know that in this rule here, we know that digit is something from 0 to 9, and digit is something from 0 to 9. So that means you can have 99, that's accepted, and 00 is accepted. So anything between those numbers is accepted by the 2-digit number rule. Yeah, no problem. And remember, uppercase and lowercases, they'll get you marks as well as numbers, as well as digits and symbols. Numbers, digits, as well as digits, symbols, and letters. They will all get you marks for your declaration in the end, as long as you declare them all. But you'd also get marks for recursion. Okay. Now recursion lets you have a number of the same thing. So here, number, what can number be? Number can be a single digit and stop. So it can be anything from 0 to 9 and stop. Or it can be a digit followed by another number, which is the rule here. So like I said, recursion, just look for the name of the function or procedure inside itself. And that's how you'll spot recursion. So there we've got digits. That means you can have any number from 0 up to infinity, basically. Yeah, you can carry on as far as you want. Now, something that you do see as well, that I get questions about quite frequently, is the use of null. Why would we use null, John? Well, if you want a terminating condition, if you want to end, this number rule accepts null on its own, which means nothing. Which means number can be nothing at all. So be careful when you're using null, because if the rule says you can have something or you can't have it, won't work. Okay? You got to be careful. Now, students ask me about syntax diagrams. How do we draw it, John? So your syntax diagram, there's only three. There's only three that you can have. So remember, non-terminals and terminals. Terminals are your rules. So that might be a digit rule, for example. And a terminal is something like, question mark in there. Flow of information, you must draw your arrows on your flow of information lines. Hello, Leon. Bit late to the party, but you're here. So here we go then. I put this in here, and this basically says a sign rule is made up of, oh, that's bad, isn't it? Is made up of plus or minus. You would have to draw one of these in the exam, yes. So for example, this is the representation of the rule as a diagram. You can have a plus or a minus. So you come in, you can take a plus, carry on, or you can take a minus and carry on. Okay, plus and a minus are terminals, so that's why they are in ovals like that. Now, syntax diagrams, we can do things like concatenation quite easily. So how do we represent this production rule here, this 2-digit number production rule? Well, we just draw it like this, digit and a digit. We have to carry on, take a single digit from 0 to 9, and we have to take another digit from 0 to 9. And because they're non-terminals, they have to go in rectangles. Now, you'll see in mark schemes, they don't include these lines on it, okay? Now, these, if I go back, they have been provided by the exam board. That is in the annex in the specification, so you should be using these with the lines on as well. Okay, so don't be put off if you see it in the mark scheme, they've not used it. It's just the exam board being lazy. Last thing we need to be able to represent is recursion. So to repeat a section, all you have to do is draw your rule and then loop back round. Okay, if you go over the lines, it doesn't really matter. Yeah, concatenation is one thing following the other. So in our digit recursive rule, you can have a single digit or as many digits as you want. This means you can have a digit and carry on with your life, or you can have a digit and go back, take another digit, 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 go back, etc. You get the point, yeah? So here you go. You might have seen this before. Doesn't really matter. I just want to show you how we would do this. So in the email address of staff at National Bank are made up of first name, followed by a full stop, followed by a surname, followed by a single digit, followed by the @ sign, followed by nb.co.uk. All first names and surnames consist of lowercase letters only and can be of any length. Produce an appropriate syntax diagram to define an email address at National Bank for 5 marks. Produce an appropriate Backus-Naur Form definition for an email address at National Bank, 4 marks. Explain why Programmers find both syntax diagrams and Backus-Naur form notation preferable methods for describing the syntax of programming languages compared to natural English. Now this here, I would like to know your opinion. Would you do the diagram first or do the Backus-Naur definition first? Diagram first or definition first? Answers in the chat, please. I'm interested to know. While people answer that, I'll just start answering the question. I'm going to have a letter, and I'm going to have A, B, C, X, Y, Z. So they're lowercase. I got digits. Digits are going to be 0, 1, 2, 9. Definition, Backus-Naur, definition, diagram. Okay. They're so similar. Definition. Okay, fine. So that's the digits, and I'm going to have my name, which is going to be a recursive rule. So here's my name rule. It's going to be a letter or a letter followed by the name, and then I've got my email. Apologies about the drawings. PowerPoint's drawing stuff isn't very good. So we're going to have a name first. Then I'm going to have a full stop. So that's the first name, full stop. Now, why can I write a full stop in my final production rule like that? Why can I write a full stop in my final production rule like that? Single digit. At nb.co.uk. Anyone know? Mosin. Non-terminal. Remember, Mosin, non-terminals are rules. John is correct. It is a terminal. No. So remember, you can have letters, you can have digits or numbers, and you can have characters, symbols. So a full stop is a symbol, so it's allowed to be that. It's allowed to be there because it is a terminal. Then you've got at nb.co.uk. Because they specified that in the question here, I'm going to put that straight in, that they must have it. If you wanted to and put that in a rule, let's say you put email in a rule, and then you just stuck like email there, email end, for example, yeah, and you put that inside this thing called email end, that would also be perfectly fine. No problem whatsoever. So how do we draw this as a diagram? What? How do you draw this as a diagram? Now it's worth 5 marks, firstly. Okay. Now I'll ask you a question in a minute. Could you put, yes, you can put full stop in a rule. Right, so for this one, for letter, right? Let's just put letter. How would I draw that rule there? What I would do is I would have a line like this. Now I really do apologise if you can't see it that well. I'll try and make it a little bit bigger than normal. A, B, C, ... I'll just put Z down there. This is absolutely crazy on a graphics tablet. I need to upgrade my graphics tablet. I really do. This is stressful. These are arrows, by the way. So that is my rule. Okay. What you're seeing is you can have an A and go down and carry on. You can go along the top and take a B and carry on. You can take a Z and carry on. But you can only have one. So digit would be the same. You can probably imagine what digit would be. It would just be a 1. Don't forget 0. 0, 1, 2. Yeah, you'd have lines on the top like that. Down here, down here, down here, down here, down here, down here. It's not my birthday. Well, thank you very much. No, second name wouldn't have to be surname. The reason being is because that person's very annoying. It wouldn't have to be surname because a first name and a surname is just letters of any length. Let me just... There we go. Okay. That person was well annoying. So that's my digits. That's my letters. So the next thing to do then is to look at, if we're looking at name, for example, okay, what would name look like? Well, it'd be a letter like this. That's a bad drawing. But that consists of a letter. Now, my question is, would you put letter, recursively called, or would you put name and recursively call it in there? What would you do? Can you see that? Just about see that. So should I replace this with name or should I leave it as letter? Omer, you are correct. The letter is recursively called. So it's going to be letter because that is what it should be in there. Okay. And the last one, to do the final one, to do this here, you would say name. Let me draw the final production rule out here. Two lines. You'd have letter, a full stop. Digit, recursively called, recursively, oh my goodness, I'm losing the will here, oh my goodness, get my arrows on there, oh it keeps doing this, I'm not right clicking, I promise, it's this tablet, arrows on, stop it. Oh my goodness. Now, what should that go in? What should that go in? Uh-oh, what's going on here? Let me report that person. What? Okay, do you need them two lines inside the rectangle? I don't think that you would lose any money. Lose any lines there. Okay, lose any marks for not drawing lines. But I would do it anyway. So I'm just trying to deal with this person. There we go. So yeah, I would. If you could, I would just draw this in the best oval shape you can because you're dealing with terminals in essence. Okay. Oh, sorry, apologies it got that messy, people. Really, I'm sorry, but that's what we're doing now. My question that I said I was going to ask you before is this has basically made me draw the syntax diagram for each rule that I've made. In other exam questions, Normally, you just draw the diagram for the final production rule itself. You don't draw out each, like the rule for letter. You don't draw out the rule for digit. You don't draw out the rule for name. So please read the question. Okay, I think they wanted you to draw out all of these here only because it came first, but it did say to define an email address. Now, because it's worth 5 marks, I think you have to do a little bit more than just producing this diagram here. Now, that's incredibly difficult to work out. So nowadays, the exam questions are a little bit more explicit because this, I think, was from the 2016 sample paper. And that's where the exam board are trying to find their balance. Okay? If your oval looks like a circle, no, they wouldn't be that tight. They've got to do positive marking. There's a fly. Look. Okay. And then the last question, explain why programmers find both syntax diagrams and Backus-Naur form notation preferable methods for describing the syntax of programming languages compared to natural English. Okay, it's a good point, Omer. That's why I said read the question, because if it says syntax diagrams, it means plural rather than just diagram. But I would go down that, right? If there's time in my exam, I'm going to do it anyway. You're not going to lose any marks for it, are you? Especially if you've got the time to do it. So the last one there, why might you prefer syntax diagrams and Backus-Naur form notation over natural English? And it's because the syntax of computer languages follows strict, unambiguous rules, but the English language can be ambiguous. 1 mark for both the comparison to syntax diagrams and Backus-Naur form, and syntax diagrams provide a diagrammatic representation which are easy to follow. Remember, a picture is worth 1,000 words. Yes, it is, apparently. So it's easier for humans to understand diagrams than it is text. All right. Backus-Naur definitions can be easily coded when writing a compiler. So you could have any of those 3 marks there. So deep indeed. All right. So here we go. Right. This one will be the last question I do on Backus-Naur form. The name of a constant in certain computer language must be either a single uppercase letter or a single uppercase letter followed by 1 or more uppercase letters or digits. This one just says produce an appropriate syntax diagram to define a constant in this language. 4 marks. Produce an appropriate Backus-Naur form definition for a constant in this language. Okay? So what I would do is I would, again, probably, most people actually went with the definition first. So that's what I'll do as well. Okay? So the name of a constant must be either a single uppercase letter or single uppercase letter followed by 1 or more uppercase letters. So the first thing I need to do is declare my upper. Hopefully I got a bit more space this time. Upper. And please don't lose a mark for something so silly as not doing uppercase letters. I'm going to need letters or digits. Digit. So digit range isn't specified, so I'm going from 0 to 9. Then I need my recursive rule, so I'm going to do that. So I'm going to go, let's go string. Right. Name of a constant can be either a single uppercase letter or a single uppercase letter followed by 1 or more uppercase letters or digits. So I'm going to say you can have a single uppercase, or you can have a digit, or you can have more than one uppercase letter, recursively called, or you can have a digit, as many as you want, recursively called. Okay, choice of 4 things there. Singles or as many as you want. Okay. Then you've got your final production rule, which is a constant. And what does a constant consist of? It must consist of first an uppercase letter. You must have an uppercase letter, followed by your string variable. Now, how do we make this into a diagram? Next thing, so we must have an uppercase letter, so that bit's quite straightforward, right? Now, when you draw syntax diagrams, first, lead in with an arrow first, okay? You must draw your arrow first. Then, what's the first thing we're allowed? Yes, Adil, that's fine. No problem with that at all. You can do that. So the first thing we need to have is an upper. Must have an upper, followed by... Stop doing that. Upper. Followed by a single case upper digit. A single uppercase digit, and carry on with your life. Or you can have a digit. Or you can have a digit instead. So that means you could go along there, branch off and go this way, and then branch back in and continue. Okay? Now, problem arises, how do we get as many upper or lower cases as we like? We need to include recursion, okay? I should have probably made that a little bit longer, so let's have a look at that. There we go. So recursion would go back up to where it splits off. And I'll put a big arrow in there. Arrow there. All right, there we go. So you've got 1 mark for the compulsory uppercase letter, 1 mark for the optional uppercase letter or digit. Now, in addition to that, I'm missing something. The name of a constant in a certain computer language must either be a single uppercase letter, comma, or a single uppercase letter followed by 1 or more uppercase letters or digits. So what have I done wrong? My printer. What have I done wrong there? Anyone spot it? The clue is on the first line, question number 7. Anybody know what I've done wrong? You have to have an upper or digit the way you've done it. Yes. Yeah, I mean, you're quite right. A single uppercase letter and that's it. So mine forces you to have an uppercase, another uppercase, or a digit. So I should be able to have just 1 uppercase. So to fix that, I'll come off here. I'll do that. Okay, so this is basically, don't draw this in the exam, like the null. I've just written null in there just to show you where that is. Okay, so I've had to put a null in there, and then in my string definition, I need to be able to put in null there. Okay, now that's perfect. Again, all the marks, 8 marks on the screen there, people. 8 marks. So yeah, Yamin, I've adjusted that now, and that should be okay. All right. 1 mark for the skip arrow, and then 1 mark for repeating the uppercase and or digit. So that's how we do it. So Victoria, okay, a constant must be an uppercase letter. So a constant could just be A on its own, right? So if it's A on its own, I take an uppercase, which is A, and then I skip it on this arrow here and carry on. So that works. I should be able to do B, A. Uppercase letter, so actually B done. And then you go to the uppercase letter again, and you carry on. So that's B, A, that's fine. What about something that's, so a single uppercase letter on its own, or a single uppercase letter, which I've got, followed by 1 or more uppercase letters or digits. So I can take as many uppercase or lowercase digits because I've got a recursive function. This allows me to have as many digits, upper and lowercase letters, as I like. So this is recursion. This is a digit rule. This is an uppercase rule. This allows you to skip on, and this allows you to recursively call it over and over again. There is the mark scheme. So look at that. Okay. Single, uppercase, digits, or uppercase letters. Wonderful. Yes, you're allowed a single digit on its own. It's not easy to see, but it's in the top of question 7, and it just has like a little random comma that you need to be able to pick up on. So a single uppercase letter, comma. English student like you should be able to spot that, no problem. Okay. So Backus-Naur, we've done that. Syntax diagrams, Boolean, and done. Okay. Right, let's just mark off what we've done. We've done all of them. We've done constructs. We've done syntax diagrams, Backus-Naur form. People were asking about software engineering and then legal. No, because we were already taking a letter initially before the digit and before the other letter. Because we've got null in there. So we have to take just an uppercase. Software engineering. Computer aided software engineering. Case tools is the name of a software tool that provides a number of functions which assist with the design, development, and testing of software. Think about this, people. The main advantage of software engineering software tools is to help you create software faster. Yeah? Dijkstra's algorithm is a searching algorithm, but they've only specified that they're doing binary search. So my belief is, because they've only specified they're doing a binary search, they wouldn't include another search algorithm like linear or Dijkstra. That's my opinion, but it's not fact. So it's up to you. Okay. Case tools. We've got CAD, computer-aided manufacturing, and computer-aided design were sort of kicked the ball rolling off with case tools, because case tools try to create high-quality, defect-free, maintainable software. And computer-aided design is software that enables you to design things electronically, right? Now this is from a mark scheme, right? Some of the functions of case tools are providing a data dictionary. Binary search pseudocode off, right? Yes, we can, yeah. Binary search pseudocode, no problem. So providing a data dictionary, you've done data dictionaries in your coursework. So remember, that was basically a table of all of the information that you're going to hold, all your variables, all your fields of your records, etc., etc. The validation methods you're going to do, descriptions of them, graphic and design, graphic and diagram production. So that could be wireframing of something, designing an app maybe, or a website, a code generator. That might be an IDE, believe it or not. Providing repositories, encapsulations, object-oriented programming. I can do that if you want me to, no problem there. Code generator, providing repositories for reusal, so that's reusing code. Providing project management. So have you ever heard of Monday.com? Monday.com? No? That's that annoying case tool basically that allows you to do managing projects. Version control, so you've got Git, GitHub, Tortoise, SVN, etc. They are pieces of software that enable you to use version control so you can go back, constantly get the ad. It's very annoying, isn't it? But they make a lot of money. Carrying out report generation, so automatic report creation of what people are doing and how things are progressing in your project. And also may include prototyping tools as well, like your fancy software for prototyping aircraft or vehicle design. So when we get into case tools, we've got two types. We've got three categories really. We've got integrated case tool, upper and lower case tool. The upper case tools are for your analysis part of your software development lifecycle, and the lower case are for the development part, the actual nitty-gritty part of it. All right. If you ever go into development, software engineering, software development, you will either be a front-end developer, a back-end developer, or a full-stack developer. Right? Full stack developers do both front end and back end development. Some front end people just focus on what the user sees, the HCI, the human computer interaction side of it, or back end. So they never even see a customer ever. They just control the databases and the repository storage at the back end. So you have to make that decision in your life. What do you want to be? Then you've got integrated case tools that kind of used throughout. All right. So examples then. Uppercase tools are diagram tools, process modeling tools, project management, document analysis, just general analysis tools and design tools. Your lowercase tools, things like configuration management tools, your change control tools or your programming tools, prototyping, IDEs, web development tools, even Wix is a lowercase tool, I suppose. Quality assurance tools and maintenance tools. Now, planning, when it comes to planning tools, the job really is to create diagrams. They have templates. You can use things like draw.io or Glyphy, and they'll create things like flowcharts. They have loads of shapes already that you can use. Microsoft brought out a package called Microsoft Visio, and the point of it is you don't have to sit there by hand and draw it out on a piece of paper. You've got very fast, rapid application development where you can change them on a very fast basis based on feedback. And we have analysis tools. So analysis is a very complex process. I'm sure you'll agree. In your coursework, it was a nightmare for some of you. But analysis is an involved process. Okay, you can record the requirements of use cases. You can sort of hone in on your specification requirements, get your aims together. You can even build something called test cases, which you set up your tests before you actually create software. So it's automated testing later on down the line. And we have software like Case Complete that allows us to record and validate requirements. So have we met our requirements? Are we near them? Are we moving further away from them? Because believe it or not, most software veers off and doesn't meet deadlines because of a number of variables. So design tools, you've got use case, a list of actions or events or steps, typically defining the interactions between the role and the system. So what does the user do to add data into the system? What does the system do with the data? How does it process it? and what would be the outputs at the end. All right. So what you're looking at on screen really is something called a unified modeling language, a UML diagram. You might have used a DFD diagram, you might have used a JSP diagram, but that's all to help you design what the system will look like, and that's what UML does. I've just shown a different one there, the one that you're not used to. Then we've got our lowercase tools. So all the collaboration features, so different members of the team can all access all of the resources. So they might even use Google Drive to access things, to look at specification requirements and things like that. If you've ever heard of Slack, Slack is like a WhatsApp for industry. It's just like a professional networking, talking, management tool. Even Zoom can do this now, where you talk to people, talk to your team, have stand-up meetings in the morning, etc. Management of what could potentially be hundreds of documents is more streamlined. That's one of the main advantages of using a lowercase tool for implementation. Design tools allow the system to be modularized, ready for implementation. Modularized being broken down into smaller parts. And also, it will also look at how the code will be structured. So we do an awful lot of planning before anybody touches a keyboard. So much planning, organization, who's doing what, who's responsible for what, etc. And then finally, tools to help prototype interfaces. So get your wireframes together. Okay, people need to know what they're designing. That's the main crux of it. Now we've got case tools. So finally, system testing. Testing is one of the most important things in the entire process. Testing takes up so much time, and it's also incredibly expensive. So we want to try and automate our testing as much as possible. They are back again. So what happens when you stream so popular, you see? What can I say? So test plans and test runs are recorded using these tools, which can then link in with bug tracking software later on down the line. Trying to get that error-free or defect-free software is very difficult, but it is more achievable by using a case tool. Okay, and you might see things like Bugzilla or Launchpad and things like that to try and weed out some of these. At the college, we've got things like maintenance software, and we basically log our jobs. Like IT services, we log jobs. Premises team, we log our jobs on there, and we get a ticket number, and the ticket number is investigated by a member of staff, and then we get updates on it and things like that. So it allows other people to take different parts of the system and work on things. So modifications in the software occurs once the software has been delivered to the customer. So we might have to go back and improve things later on. So we might have a maintenance contract once we deliver a piece of software, and that's where quite a bit of money comes in for us, really, because if it's a bespoke piece of software and we've made it, then we might have to get involved. So it would be helpful to developer if the software recorded what we've been doing, so while it's live and running. So we have analytics normally embedded in, and it sends data from millions of users potentially back to us. Okay, not so much detail a deal, but you need to know the parts of these things. So like planning, analysis, design, what tools would be used, implementation, testing, maintenance, what things would be used, the deal. All right. Main benefit to maintenance software is that we've got auto login, error reporting, and also auto ticket generation and root cause analysis. So where are the problems coming from and what is the root cause of those problems, so we can kind of fix it. And that's why you always get app updates and patches coming out. Was done with A2 nearly like 3 years ago. Yeah. The famous people, the old school people are coming back. So here we go, the main advantages of using case tools. We've got increased speed through the life cycle, increased accuracy in the software production, reduced lifetime maintenance. So the problem is here, although we don't need to maintain as much, it frees up some more time. We're not needed as much, so it means we're not gaining as much money, as selfish as that is. So yeah, we also can create better documentation. Then you've got programming is in the hands of non-programmers. So some case tools allow programming ability. So for example, Cedar, what we use is we can program that only a small amount internally, so we can make it do what we want it to do. So things like Wix and stuff like that are taking over as HTML generators. Although you'll speak to people and they'll say you can never truly get a good website out of Wix, but so there you go. So disadvantages of case tools, tool mixing. So they don't always link together. You've got different tools coming across. You've got to learn all in different tools. There's a learning curve, I suppose. And you've got to fit that in. You need time to learn technology. And then also, you've got the cost as well. Okay, there's a specific cost for the software. Yeah, that's right. They don't do it at uni. You don't get this kind of service at university, do you? 9 o'clock on you in the evening after you've been in work all day. Now then, there's a summary of case tools. That's come from a mark scheme, but that's in there for you to have a look at. And then the next bit really is IDEs, integrated development environments. We've been using Visual Studio for Visual Basic.NET, Python, C# on the T level now, PHP, HTML and CSS. That all goes into something called Atom that we use. These IDEs are really to help you develop faster, write code. The code editors, that's all they are. So IDEs have the benefits of coloring of syntax, automatic line numbering, which is easy to spot a problem, especially if you paired programming. You link it, you've got linked constructs, so automatically you'll write if, press enter, and it will produce the rest of the if statement for you. Automatic indentation is done. It'll finish ends of lines of code for you. So if you put in a speech mark, it'll finish the other one off. And believe it or not, it saves a lot of time. It really, really does. And then you've got highlighting of syntax as well. That's also the final part. Makes it easy for you to read and see. Another advantage is the fact that you can debug quite easily by putting in breakpoints. Automatic error checking is provided, and it can produce error reports when you try and compile or interpret your code. And then you can put breakpoints in there, so them little red dots in Visual Studio, and you've got stepping through your code as well, so you can basically see each line of code during execution on the CPU, which is incredibly impressive. Okay? And I'll just reiterate, program version management. Okay, version management is incredibly important, and I'll tell you for why. I've seen students that have accidentally deleted their code, edited or changed something when they needed it, got rid of something they didn't think was important, but now they think it's important. So that's why we normally use GitHub, something like that, to basically have branches from our main system, and then we commit the changes to those things. All right. Sometimes you'll see standard version management where you've got the number at the end. So 1.0 would typically be the first release of the program, 2.0 for major changes, etc. 1.1 or 2.1 would be a smaller minor change. The release year might be on there as well. And you might even have codes on the end which help the developers understand which version that is. Like if you look at your iPhone, the version's crazy on there. They've got, I don't know what versions we're on nowadays, but there we are, version management. Okay, people. What I would say at this point, I'm sure a lot of you are fatigued. We've gone through quite a lot of stuff there, to be fair. Now, on Friday, I can go through the rest of the stuff. I can do some binary searching, and I can finish off Boolean expressions, and I can also do the economic, moral, ethical, legal stuff as well. So I think we'll finish there, people, for today. We've been going for 2 hours and 9 minutes. It's not a bad do at all. Remember the exam's on Monday. Maximum effort now, people. You are really, really close now to the end. So, as always, thanks for joining me. I do appreciate you being here for it. There will be a live stream for Component 2. If you've got exams on Friday morning, electronics, is it 2 hours long? What do you think the algorithm will be? Usually a searching or sorting algorithm. Yeah, my personal opinion is it's going to be a searching algorithm, the binary search, but I'm not too sure. I think you might get an algorithm question as well, 2 hours and 45. Must be WJC, yeah? 2 hours and 45. Wow. Okay. Well, I'll be on hand Monday morning before the exam. If you want to come in on Monday morning, I'll try and make myself available before the exam. Nathan, yeah. Spyros. Oh, right, okay. I didn't go through that, no. I was trying to find an example of recursive binary search. It's on the AS paper. I need to get that tomorrow from exams because it's in the paper. I don't have the electronic version of it, but I will get it. Hello, Rayhan. I remember Rayhan. Now you mention robotics, it makes sense. Well, I don't have favourites. I dislike everybody the same. This is true. All right, people, keep up the revision. Email me if there are any problems. I will see you on Friday, but keep going. Good luck. And I'll see you again soon.